Today we are going to discuss decoding of LDPC codes. So, to start with, we will first take a simple example of transmission over a binary symmetric channel, and we are going to talk about a bit flipping algorithm to decode LDPC codes. And then in the next lecture, we will talk about probabilistic decoding algorithm based on belief propagation. So, we will consider two cases today. First, where there is only one error has happened, and second, where there are two errors have happened. And we will show how we can correct these errors using LDPC codes. So, recall this is an example of a low density parity check code of block length 20, the column weight is 3 and row weight is 4. We will first define few terms and then we will come to the decoding of that. So, first thing we will define is what is a parity check set. So, what is a parity check set? It is the set of bits that are participating in the parity check equation. So, set of bits that participate in a parity check equation, they constitute a parity check set. So, for example, if you look at this particular parity check equation, now these are the bits that are participating in this parity check equation. So, these bits will form a parity check set. If you look for example at this particular row, now this bit, this bit, this bit and this bit, these are the 4 bits that are participating in the parity check equation. So, these bits will form a parity check set. So, what is a parity check set tree? It is a graphical representation of the parity check set in a tree like structure. How? We will explain. So, any arbitrary bit is represented as node of the base of the tree. There is a line arising from this node and each of these lines represent one parity check equation where this particular bit is participating. So, each line arises from the node and it represents one of the parity check equations or one of the parity check sets where this particular node is participating. Now, other nodes in these parity check constraint are represented as nodes in the first tier of the tree. Now, what do I mean by this? So, let us just look at. So, let us say I have this node, first node, calling it node 1. Now, this node participates in 3 parity check equations. You can see 1, 2, 3. Go back to our. So, we are looking at first bit, it participates in this parity check equation, this parity check equation and this parity check equation. So, there is one line corresponding to each of these parity check equation. Okay. Now, in this parity check equation you can see which are the other bits participating. So, bit number 2, bit number 3, bit number 4. So, how did we write that? So, the other bits that are participating in the parity check constraint, they are written like this. So, 1, so this is one parity check constraint and 2, 3, 4 bits are participating. Similarly, if you look at here, this bit number 5, 9 and 13 are participating in this particular parity check equation. So, that is represented by this. So, that is what I mean when I said other nodes are represented as nodes in the first tier. Now, line arises from tier 1 to tier 2 represent the other parity check constraints containing bits on tier 1. So, this is my tier 0, this is tier 1. Now, what are the connections coming here? These are the parity check constraints involving these bits, involving 2, involving 3 is here, involving 4. These are the parity check constraints. Okay. So, this is how I am drawing my parity check set tree. So, again pay attention to this parity check matrix. Let us label each of them like this, let us say 1, 2, 3, 4, 5, 6, 7. Let us just label these columns. So, that way it will be easier for us to refer to them. Similarly, I am labeling these rows. So, you can see there will be 15 parity check sets, each corresponding to each of the rows. Okay. So, let us look at the parity check set. So, let us first look at this first parity check set, which corresponds to this first row. So, note here bit number 1, 2, 3 and 4. These are participating in the parity check equation. So, that is why this first parity check consists of 1, 2, 3 and 4. Similarly, parity check set 2. If you look at second parity check equation, this bit number 5, bit number 6, bit number 7, bit number 8 are participating. So, then parity check set will have 5, 6, 7 and 8. Similarly, parity check third has 9, 10, 11, 12. So, we can take any example. Let us just take this one, 8th one, bit number 3, 7, 14 and 18, 3, 7, 14 and 18. These are participating in the parity check equation. So, bit number 3, 7, 14 and 18. So, this is how for each of the parity check equations we create this parity check set. So, there are 15 such parity check set for this particular example. And how do we draw the parity check set tree? As I said, we pick one bit. Let us say I picked bit number 1. Now, bit number 1 appears in which parity check set? How many parity check equations? Look here. Bit number 1 appears in this. Bit number 1 appears here. Bit number 1 appears here. That is it. It appears in these 3 parity check sets. So, we are going to draw 3 lines corresponding to each of these parity check sets. So, that is what we have done. This is one line, this is another line, this is another line. Now, next what we have done is we have written all the nodes that participate in the parity check set. So, if you look at this one, in addition to 1, the other bits are 2, 3 and 4. So, that we are writing like this 2, 3 and 4. Similarly, here bit 5, 9 and 13 are participating in addition to bit number 1. So, these are 5, 9 and 13. And here 1, 6, 12 and 18 are participating. So, then we have 6, 12 and 18. So, this is our tier 1. Now, how do we draw tier 2? Now, look at each of these bits, look at 2. Now, 2 appears in which? 2 appears in parity check set 1, 2 appears in parity check set 7, 2 appears in parity check set 12, right. Now, this 2 appears in with parity check set 1, this is already captured here. This is already captured here, that 2 appears in parity check set 1. So, what are the other 2 parity check set? This is one is this, other is this. So, 2 appears with 6, 10 and 17. How do we show that? So, we are showing this by this particular edge. How do we show this parity check set? 2 appears with 7, 11 and 16. How do we show that? We show that using this. Similarly, we do the same thing for other bits. So, for example, bit number 3. Now, look at bit number 3. Bit number 3 appears in parity check set 1, it appears in parity check set 8, it appears in parity check set 13. Now, this parity check set 1, that is already captured because that is this one, it's already captured. So, what are the other 2 parity check sets? The one involving 3, 7, 14 and 18. So, this is 3, 7, 14 and 18, that is this one. And the other one is 3, 8, 13 and 19. So, this is this one 3, 8, 13 and 19. Okay. So, we are basically connecting by edges all these parity check sets. So, that is how we are representing parity check set tree. Now, we can do this with other bits as well. We can, for example, instead of making 1, if I can make this as 2 and construct a tree around this node 2. Same procedure. Now, let us look at how we can correct error. So, we are considering a binary symmetric channel. Again, recall what is a binary symmetric channel. So, there are 2 inputs 0 and 1, 0 and 1 with probability 1 minus p, you receive the bits correctly and there is a crossover probability of bits getting flipped. So, let us consider that we have transmitted this information, we have transmitted this coded sequence and what we received is this. So, there is an error in the first bit location. Now, how do we correct this error? So, to decode this, what we are going to do is, we are going to construct a parity check set tree around each of these bits and use that for our decoding purpose. So, let us see how we do that. So, the first step is we represent the code using parity check set tree, and we have explained in the previous slide how this parity check set tree is constructed. So, this is the parity check set tree for the bit number 1, and remember this is the parity check set corresponding to this, we have drawn this parity check set tree. Now, what we are going to see first check is whether all the parity check sets containing bit number 1, if they are satisfied. If they are satisfied, it is likely that bit number 1 is received correctly. If majority of them are not satisfied, it is likely that bit number 1 is an error. So, let us see. Now, which are the parity check sets in which bit number 1 is participating? That is this one and this one. Now, note in our example, there was a single error in bit number 1 location. So, all other bits were received correctly, only bit number 1 was in error. Then what is going to happen? this parity check set would not be satisfied because this bit is in error. This will be satisfied, this will be satisfied. This will not be satisfied because this particular bit was in error. These are all satisfied. This will not be satisfied. Again, these are all satisfied. So you can see all the three parity check sets involving bit 1 are not satisfied in this particular example. So all the parity check sets containing 1, 6 and 11 are violated. Now what does that mean? It means that there is a very large likelihood of this particular bit being received in error. Hence, what do? Then we are going to flip this bit 1, whatever this bit was, we are going to flip it and then again check the parity check constraints. So earlier this bit was received as 1, we are going to flip it to 0 and again try to check the parity check equations. Now note that when we flip this bit is now no longer in error, these bits are no longer in error. So then this parity check constraint will also be satisfied. Hence we are able to correct single error. So when we recompute the syndrome, we will see that all the parity check constraints are satisfied because there was only single error which we are able to detect and we were able to correct it. So hence the first bit will be decoded as 0, and same procedure we will follow for other bits as well, and since there was no error in other bits, so all the parity check sets involving those bits will already be satisfied, so we will be able to successfully decode it. Okay. Now let us look at the case when there are two errors. So the same transmitted code word we have considered. In this case now we have considered there are two errors in bit location 1 and bit location 2. Now let us see how our LDPC decoder will be able to decode this. So again we follow the same procedure, we draw the parity check set tree with each node at its page. So we start with node number 1, we construct the parity check set tree. And these are the parity check set, 15 parity check sets corresponding to the parity check matrix given to us. Now in the first step what we do is we check the parity checks containing bit number 1 and we see if all the parity check constraints are satisfied. So what are we going to do? We are going to look at all these parity check sets which have 1 in them. So this is our parity check set 1, 6 and 11. Now will this be satisfied? Yes, it will be satisfied. Why? Because this was also in error and this was also in error. So this parity check equation will be satisfied because two bits are in error. Okay. What about this? This parity check set will not be satisfied. Why? Because 5, 9 and 13 were received correctly, but 1 was not received correctly. So this parity check set will not be satisfied. Similarly here 6, 12 and 18 are received correctly, but 1 is not. So then this parity check set will not be satisfied. So what we have seen here in the case of double error is 2 of the parity check set involving 1 is not satisfied, whereas 1 is satisfied. Now what does that tell us? It tells us since majority of them are not satisfied, it is likely that bit 1 was in error. So we are going to flip it and try to do the same thing again. So since 2 of the parity check sets are violated, it's likely that bit 1 is in error because majority of the parity check set containing 1 are not satisfied. So what do we do if majority of them are saying they are not satisfied? We are going to flip that bit. So we are going to flip the first bit from 1 to 0 and again recompute our parity check constraint. So let's do that. So this bit has been flipped. Now if this bit has been flipped, what's going to happen? If this bit is flipped, now this bit has been corrected, but 2 was in error. So this parity check set, which was earlier getting satisfied, is now not getting satisfied. What about this? It is getting satisfied. What about this? It is getting satisfied. So 2 of them are getting satisfied, while 1 of them is not getting satisfied. So then first iteration is not enough to decode this bit, because parity check set first fail. There were 2 errors. So first iteration is not sufficient to correct the errors. So then we will go to the next tier. So next iteration we will check parity check set containing bits in the first tier of the parity check constraint of the tree, and we will see if they are satisfied. So what we are going to do is, we are going to go into the first tier. So we are now going to look at these bits, and we are going to see if the parity check sets involving these bits 2, 3, 4, 5, if the parity check sets involving these bits, are they getting satisfied? If they are getting satisfied, fine. If they are not getting satisfied, then we will again have to flip the bit to make them satisfied. So this is how we are going to proceed. So let's look at second iteration. Now what we are going to notice is that since bit 3 was not in error, bit 3, 4, 5, 9, 13, 12 and 18, these will get satisfied. So if you go back to the parity check set diagram, this was not in error, and this involves 18, 14, 7, none of these were in error. Similarly, this involves 8, 13, 19, these were not in error. So all the parity check set containing 3 will be satisfied. What about 4, 11, 15, 19, they were not received in error. Similarly 4, 9, 14, 17 were not received in error. So this parity check sets will be satisfied. 5, 6, 7, 8, this will be satisfied. 5, 10, 15, 20, again these will be satisfied. Similarly 9, 10, 11, 12, no error in any of the bits. So this parity check equation will be satisfied. Similarly 17, 14, 4, so this will be satisfied. 13, this has 16, 15, 14 and 13, none of the bits are in error, so this will be satisfied. Then 3, 8, 19, 13, again this will be satisfied. What about this? 6, 5, 7 and 8, none of those bits are in error, so this will be satisfied. This will be satisfied. But what about this? 6, 2, 10 and 17. Now this bit is in error. This bit is in error. So this particular parity check equation will not get satisfied. What about this? 12, 9, 10, 11, this will be satisfied. 12, 8, 16, 20, this will be satisfied. Similarly 18, 17, 19, 20, this will be satisfied. 18, 3, 7, 14, this is also satisfied. What about 2? This will be not satisfied, and similarly this will be not satisfied. So what we can see is the parity check sets involving 2 is not getting satisfied, because here there was 2, here there was 2, here there was 2, it's not getting satisfied. 2 of them are not getting satisfied, and the third one is this one, which involves 1, 1, 2, 3, 4. This is getting satisfied. This is also not getting satisfied, because 1 was corrected, 3 and 4 are correct, so this is also not getting satisfied. So what we notice is parity check sets containing 2 are not getting satisfied. Then in that case, what do? We are going to flip the bit. So, parity check sets containing bit 2 are not getting satisfied. Again, one of the constraints containing bit 6 has bit number 2 and it was not getting satisfied. So, bit 2 was common in all the parity check sets which were not getting satisfied. So, what we do is we think that second bit is an error and we are going to flip the second bit. So, we flip the second bit was 1, we flip it to 0 and we are going to recompute all the syndrome. And now we notice that the parity check constraints are satisfied because the 2 bit was an error. After we have flipped it, we will see that all the bits involving 2, all the parity check sets involving bit 2 are now getting satisfied and hence we are able to correct all errors. So, if there are 2 errors, you can see that one iteration was not enough, we had to go for 2 iterations. Okay. Now, we go back and check at 0th tier and we see that at 0th tier also all the parity check sets are satisfied. So, hence we have successfully decoded the first and the second bit to be zeros and all other bits were received incorrectly. So, there is no error. So, then what the decoder does, it basically computes all the parity check sets and then changes any bit that are contained in more than a fixed number of unsatisfied parity check equations and then we recompute the syndrome, recompute the parity check constraints and hopefully by flipping the bits which are common in most of the parity check constraints that are getting violated, we will be able to finally correct those errors. And each time after we flip the bits, we recompute the syndrome, check whether the syndromes are satisfied. When all the syndromes are getting satisfied, we have successfully decoded the LDPC code. And since this size of the parity check set is small, this decoding is reasonable. It is not very hard, and we can also do this process parallelly. We can have for each parity check tree for each of these bits, and we can try to do this decoding in a parallel fashion. And again, this relies on the logic that a bit that is appearing in most of the unsatisfied parity check equation, that is most likely culprit. That is the one which is appearing most likely to be in error, and we are flipping that bit to correct it. Okay. So, with this I am going to conclude our discussion on decoding of LDPC codes over a binary symmetric channel. We will continue the discussion on decoding of LDPC codes in the next lecture by discussing the probabilistic decoding algorithm. Thank you.